Okay, it's my great pleasure to introduce today's speaker, Astrid Nieße. She is a professor for digitized energy systems at the University of Oldenburg in Germany, and she's been there for quite a long time. Before that, she was at Leibniz University from 2018 to 2020. She got her doctorate from Oldenburg in 2015. Her thesis was on distributed algorithms in the field of decentralized energy systems. And she's going to talk about cyber-physical energy systems. So I've been working with Astrid sort of on and off as both of us are members of Sig Energy, and she actually took over from me as the editor of Energy Informatics Review. So thank you very much for doing that. And also thank you for doing this talk. Looking forward to it. It's all yours.
Okay, thanks a lot, Keshav, and thanks for the nice introduction. So very happy and sorry for not attending physically, actually. So we will definitely do that at a different occasion. So I have the honor to talk a bit about challenges in cyber-physical energy systems. I'm quite sure that when I saw the list of speakers that already have been here in this a lecture series, that you already heard a lot of challenges in cyber-physical energy systems. But I come with the specific topics of software agents and data. So hopefully that will be interesting for you. So my talk will be on 3 topics, actually. First, on cyber-physical energy systems, the very short introduction on the topic, then multi-agent systems and data as a last point. So threefold, but not with the same parts. But there is a different view on that. So the very first thing is a little bit on buzzwords and bosses. The second one on visions and excitement, actually. And the last one is on pain. So I hope that will be entertaining for you as well. So why am I talking about buzzwords, actually? When I've been starting to work in energy systems, there was one word actually coming up, and the following happened. So this is a nice figure that my sister drafted when I told her a specific situation. So my boss, former boss, Christoph Meyer, who died far too early, he came from a conference and said, all the stuff you are doing in energy informatics is now called smart grid. And we were like, oh no, yet another buzzword. What the hell is this? And we all thought we're doing serious science. We don't need this buzzword stuff. And I always like to tell the story because I understood in the end that buzzwords have a meaning, because a lot of people now understand what is meant by all these energy informatics stuff, because we have some words that help to understand and help to explain stuff to people. So even I was a little bit well, not so interested when this term of smart grid came up. I nevertheless understand, meanwhile, that this is important. So let's talk about cyber-physical energy systems. We're talking about the field of critical infrastructures. We all need energy systems for our basic functioning of our systems, but we know that they are special, quite special challenges coming from cyber-physical energy systems. For example, phenomena and instabilities can spread in short time. So when it comes to some instabilities, for example, in the southern part of Spain, we can see them in the northern part of Germany or somewhere in Scandinavia. So that's quite interesting. And we see these effects even between the different parts or layers of the system. So they are connected systems, both on the information side and on the electrotechnical system layer. And these instabilities, they can even cascade in real time. And what we see now is that we have these cross-sectoral effects. So there might effects that come from information technology, and we see the effects in energy systems, electrical systems. There might be some effects on gas systems as well. So everything is interconnected, and that is why we talk about complex systems of systems here. And digitalization of these systems, of course, comes with even new challenges and more challenges, like security, complexity, and of course, regulation, what we definitely need in these systems. But of course, there are new challenges involved here. Then the last thing I want to point out here with respect to the challenges are the multi-criteria optimization problems that we see here, especially in very different areas, for example, monetary goals, technical goals, political. And this means that we even see, especially in the last years, very prominent examples for terroristical effects that show off in the energy system in the end. And on this system that is actually running and functioning for a long time span, we are doing this fundamental transformation towards post-fossil renewable energy systems. And that is something that you get a little bit of respect when you dive deeper into these activities. So these are the challenges. And then if we want to break down, and the stuff I would like to talk about are three things. First of all, we have to handle the complexity that comes out of these intertwined systems of energy and digitalization system. Then we have a lot of stuff that is in the area of adaptivity, where we want to grab the flexibility potential of all the different components and all the actors that are in this system. And the last thing is that with the system, of course, we want to do a transformation that is not funded by some state agency or something, but that works because there is a lot of innovation in it. So the innovation potential within the transformation towards a renewable and post-fossil system is something that we want to foster with digitalization as well. When you ask me and all the contributions me and my group can do from a digitalization perspective, with most people being computer scientists, but not all of them, of course, some electrical engineers, and meanwhile we even have some people from the social scientists, because we are in the social technical area here. So I will talk a bit about these three challenges now, and the first thing is handle complexity. So let's have a look at handling complexity. You see a very sketchy example, so just a small example of an energy system here. And we see that complexity comes with a lot of new challenges as well, like restructuring the system. So, for example, we have segregation and integration, new components coming in and dropping out of the system. And we cannot control that all of the time, because we want to be very dynamic. That means that we have to be adaptive. We have a scalability issue here, because, for example, if you take all the small PV plants, you either want to control them or know nothing about them. But if you want to control them, there is some scalability issue in there. Of course, safety and security is an important issue in digitalized systems as well. So it is here. And then we see the aspect of relocation of functionality and integration with existing SCADA system. That means that on the one hand, we do have existing systems that control the systems. That is the existing SCADA infrastructure. But on the other hand, we have this distributed system where a lot of controllers are out there in the field, and they have a specific function out there. And sometimes we have the need to transfer one functioning to a different location. So relocation of functionality is quite interesting here. A new challenge, an interesting approach here. Compatibility and real-time requirements, data analytics, and effects across sectors are topics that are quite relevant. And if you, for example, Kisha, I've already mentioned the ACM-EIR, if you have a look at what kind of scientific works are presented there, you see a lot of these address the fields that are shown here. So they are relevant for the field of energy informatics, where I am actually working in. So now let's go, yeah.
Question there about the previous slide, the one which had all these different requirements. I mean, do you feel that the system is now over-constrained? I mean, if you want to meet all of these at the same time, doesn't it mean that there will be some trade-offs? It seems very many requirements.
Yeah, very many requirements actually. So, but I think it's typical for a systems of systems perspective on the one hand, but it, on the other hand, motivates for solutions that separate the different aspects of the system. And that is actually the reason why we try to separate the system geographically sometimes, but in terms of actor roles as well. So, for example, you said that in my dissertation quite a while ago, I worked on distributed control. This was actually in the area of virtual power plants. That is one approach to take some function out of the system and try to control it separately. So there are a lot of approaches different aggregation approaches that should help in this system. But of course, it is an over-constrained system. So it's not easy to have this one control system that will help. And what comes even on top is that it is not wanted from a regulatory perspective, at least in the European Union, that all of these requirements and all of these system control aspects are fulfilled by one actor. We don't need that. We don't want that actually, because we don't want to collect all these data with one actor out there.
Okay, thank you.
Yeah, thanks for interrupting, Kishaf. And if there are any questions in the group, you simply have to step in because I cannot see all of you. Okay, so over-constrained system. I already said that adaptivity is of major importance here. And this brings us actually to the point of multi-agent systems and kind of the key part of this talk for today. So I will talk a bit about multi-agent systems. So multi-agent systems can be seen as one part of artificial intelligence. Artificial intelligence in general, and you see here that this is a quite old definition by Marvin Minsky, 1966, that simply says that artificial intelligence helps to make machines do things that would require intelligence if done by human beings. So that is a definition that is not typical if you look at the discussions on artificial intelligence by now. So we see a lot of work in the area of deep learning, that is the inner circle here, or machine learning, but we are now in the area of distributed artificial intelligence, and that is in in the outer circle of this definition. So software agents are part of distributed artificial intelligence, just to show this. So what do I mean, distributed AI? This is part of AI research dealing with development of distributed solutions for complex and large-scale problems. And an agent is a very, very simple kind of abstraction of, for example, components or specific tasks in a system. An agent, a software agent, is able to sense in the outside world. It is able to deliberate on the sensor input, so planning stuff. And an agent is able to cooperate and in the end act out there in the field or within an agent system. And the technical basis for distributed AI are actually multi-agent systems where we have the software agent as intelligent, autonomous software, and they are able to communicate and interact with other agents with special characteristics. And of course, these agents now, when we come back to the definition of artificial intelligence with the different layers within this approach to AI, these agents might involve learning or trained models as part of how they deliberate on problems that they want to solve. So sensing in the outer world, then making, for example, a training phase based on these data and later on acting in the world and having this kind of feedback loop is actually a model that is used quite often in areas of reinforcement learning, of course. So when you now go to an upper layer, where do these agents come from? I already said that agents are a means for abstraction, and the general idea is to have these very simple agents in complex systems. And a very well-known example for that are always fish swarms or flocks of birds, where we see some effects that we wouldn't expect when having a look at the simple rules that the single, for example, fish understands and knows about. So, for example, if you have a look at one of these fish in this fish swarm, the fish may not even be able to see the predator that is coming up, but nevertheless, at this one fish reacts to what is happening directly in its environment, the fish will somehow be able to avoid being caught by the predator here. So what comes out is kind of complexity that you see from the outside world, although the complexity is reduced for the single agents. So reduced complexity by simple agents. And for the overall system, we see a complex system response. And that is what emergence is about. So the term emergence means the overall system shows a reaction that we could not expect from the simple reactions from the simple units that we have in these systems. So we are now in this area of self-organization, and self-organization, for example, in this area can help us to avoid single point of failure problems by using it for distributed control. So if we divide a task that we have to solve to a huge group of agents and they solve it in a cooperative manner, it is typically more stable and more robust. That means we do not have this single point of failure problem where when one fish is actually caught by the predator, we do have a huge problem. Of course, from the perspective of the single fish, it's a different story, but that's actually not what system performance in the end is typically defined as. Okay, so now sometimes there are different aspects discussed when talking about agent-based control or agent-based simulation.
Chris, I'm glad that you brought up that this is a gray area, because I think this is one of the kinds of gray areas the courts have.
Astrid, please continue, sorry.
Okay, that wasn't a question for me?
I don't think so. Yeah, sorry, please go ahead, yeah.
Oh, okay, great. So when we apply agents in energy systems, we typically are in this area of agent-based control. You see it here on the right-hand side. So I need my pointer here. So you see it on the left-hand side, where you see some agents representing components from an energy system. So the outer part here are components in the real world, and they are modeled, these components are modeled and abstracted from by these agents. And now these agents are able to control, on the one hand, something out there in the field, for example, this cooling house, and on the other hand, they are able to communicate. And we use this kind of system layout quite often because it's more easy actually to have this abstraction of software agents and not having a detailed look, for example, if we do have an electric car or if we do have some kind of only battery storage. So this example is quite obvious. There is a battery storage on the one hand, or there is a car, and we do not need to know these details. We just have to know for the energy system is a flexibility in terms of a battery is available from time to time. So the specifics, the technological specifics are not so important. So agent-based control is concerned with this kind of system layout. On the other hand, we see agent-based simulation, and agent-based simulation is very often used in the social sciences to understand how human people interact, how they behave, how behavioral changes might occur over time and within specific groups. So this is a different area of research on the one hand, and it shows, of course, other challenges. So it's used to understand interactions between people, between human beings, and it helps us to design systems. And of course, that is something that is quite relevant as well. But now, when it comes to energy systems, this clear separation of agent-based control and agent-based simulation does not really work anymore. Because in energy systems, we always start with simulating stuff. We are in a safety critical system. We are not allowed to directly have a system out there in the field. Typically, this is not a good idea. We need a lot of simulation and verification and maybe even certification before we can transfer our components to the field. So we typically start with agent-based simulation and then go to agent-based control in the field. So what does this mean now? Where can we use it for? So for example, we use self-X agents, for example, self-organizing agent systems for use of decentralized flexibilities. For example, we could use multi-purpose operation management in a swarm. So I will come to an example of that later on. We could use it for stuff like decentralized redispatch. If you're not familiar with energy systems in detail, that you might not understand, it's just one of these examples. Something that is very easy to understand is a black start problem. So let's think about a huge blackout. So you do not have any power in your neighborhood anymore, because there's some kind of problem somewhere in the grid. But you do have a lot of, for example, photovoltaic plants and batteries. And it would be quite nice to have a startup of the local energy grid by using these components, by using, for example, the electric vehicle charging facilities, the batteries, or the photovoltaic plants to start the distribution grids from the lower levels to the upper levels again. And we could do this actually with software agents. So by now, we worked a lot in this area, for example, addressing the challenges that come from an algorithmic point of view. So for example, we developed algorithms in this area as distributed algorithms. And with me, so there are a lot of colleagues in Oldenburg. It's not only from my group, but actually a lot of energy informatics colleagues. We are 4 in Oldenburg by now. And of course, some that already retired. So it has a long tradition to work on the algorithmic challenges. Then we set up an appropriate agent framework that helps us from the design phase to the field. So if we want to implement these agents, we can use either a Python or a Julia-based agent framework to do the simulation and later on control in the field. We working on the co-simulation challenges, so how to model the communication infrastructure together with the energy system that we are interested in. And we worked a bit on the transfer to the field challenges that we see, and that is something that I want to come back now to the battery storage swarm in a field test. That is the first example that I already mentioned here. So battery storage swarm in a field test. So when we look back, we started some, there's a question, Keshav?
Sorry, yeah, I just wanted to quickly ask you this. When you talk about these self-optimizing distributed control agents, such as the ones that you mentioned, the swarm of fish or birds, one question is that when you have these swarms, at the local level, they're not aware of global objectives, right? So for example, in your power system, you have a global objective of a certain frequency that you tightly control between ±5% or something like that. How do you communicate global objectives to local optimizations?
Yeah, very interesting topic and something that I'm deeply interested in. So we actually work on different examples. So for example, one approach that we take is that the agent for itself has a local objective and local constraints. So it has to follow the technical constraints of the component that it represents, for example, the battery. So that is the local stuff, the local constraints. The local optimization would be something like maximize the financial outcome of the operation. But then, of course, there's this global goal, for example, as you mentioned, frequency control, or something that is less time critical would be a virtual power plant scheduling problem. So schedule a huge amount of component in such a way that they show an aggregated behavior we can sell to a market. That is something that can be done, but we then can communicate this global goal to the single agent. And the example algorithm that you can see here that a colleague of mine developed in his doctoral project here, this is an algorithm that actually allows each agent to elaborate if, after considering its local goals and local constraints, it could deliver something towards optimizing the global optimization goal. And then there's a kind of, well, it's similar to a gossiping protocol, consensus-based protocol, where the agents then are able to go into the direction of the theoretical optimum. This works quite well, but of course it's communication intense then because it's a gossiping-based protocol, but it guarantees to terminate and to converge into the direction of the theoretical optimum.
Right, okay.
Okay, so I would love to take the opportunity to do a little bit of a time warp as well. So what has been done in this area so far in my environment? We started actually in 2012 with a huge research project called Smart Nord, and that is where we used agents with a quite courageous approach then, because we said we are going fully dynamical here. So there is no centralized control at all. Everything is done using coalitions. So if you're familiar with the area of game theory a bit, that is where the agents fully decentralized decide on how the coalition set up. And we tried this approach for virtual power plants. That was quite early and was actually far from what could be done in the field, is still not applicable to field approaches. But it was very interesting from a fundamental research point of view. So that's why I was able to do my PhD in that project. Then in 2015, we still thought it's a fantastic idea, let's do a startup, and we got some funding for that. So we started a company, actually, me and 3 colleagues, with some money we got from a funding agency for this kind of innovative projects that might be a good business idea in the end. So we started to do that, but actually it did not work in the end. So we were far too early. And the reason for that was, beside many other problems, like, for example, we were 4 people and all of them with family. That's an interesting approach for doing a startup. I'm not so convinced on that. In the end, it was the problem that flexibility was worth nothing in energy systems by then. So still flexibility is paid only in in some parts of energy system control. In 2015, it was not at all. So then we extended our view in 2018 and worked on system operation and resilience. So more from a really critical energy system point of view. So back to fundamental research here. But then an interesting thing happened. Industry requirements and questions from industry came up. They said, agents are a cool concept, so we need them. And we started somehow to elaborate and discuss with our industry partners which specific use cases would be interesting for agents, because we did not want to implement agents that were not needed in the end. So actually 2 years ago, we had a field trial for frequency containment reserve finally, and we successfully finished it. So you just here see the microcontroller technical realization from the software agents that we had. This is in the laboratory, and exactly the same hardware was taken out to the field, and the agents were able to control flexibility in the field. And this is the concrete example. And if I got it right, Keshav, I should talk about 45 minutes, right?
Well, we should end at about 10 to 2, so that we could 10 minutes before the next hour will be 10 to 3 for you, because there's another group coming in and we want some time for questions.
Perfect. Okay, yes. This will work out perfectly fine then. So this is an example that could explain quite well how we work with software agents and where the current limitations are in the end. So what you see here are these examples of software agents, and again, they represent components out there in the field. So we call these agents a swarm, because they are able to communicate and they are able to optimize the individual components that they represent on the layer of the physical system. And the example we set up here was that all these components that we see out there already do have a purpose, they already do have a functioning. And what we see here are that all of these components somehow have batteries or show batteries. And these batteries are used in industry to do a local peak shaving. So you see here load over time. Sorry for the German left in here. So, and it's depicted very easy. You see at some point in time, the load is in this red area, and this simply costs money. So the system is as such that these short-term large loads are quite expensive for the industry partners. And that is actually the reason why they buy these batteries. and they install these batteries only for this small purpose of taking out this peak load that would be quite expensive for them in the end in terms of grid usage fees. So that means that these batteries are already out there, and the industry says, oh, nice batteries, we do have them, and we do peak shaving with them. From our perspective now, it's quite sad that these batteries are only used for these peak shaving purposes, because they are important components for the energy system transformation in general. We need them if we want to go to fully renewable energy systems. And they, of course, have a lot of components in them and resources that we value quite high, and that we want to use these resources in such a way that it's best for the overall system. So we said this is a nice example where we have this multi-purpose settings for very important components in an energy system. So our idea was, now let's first take this approach of peak load reduction, local peak shaving, very serious. We may never have a situation where this cannot be fulfilled. But if we set up an agent system that guarantees that these local peak shaving will always work, the remaining flexibility can be used for other stuff. And that is what the agents actually do. So they show this second optimization goal with a lower priority, of course, because first of all, the local goal of local peak shaving has to be fulfilled. But then we take this approach to an upper level. The agents aggregate this flexibility, and it can then be taken to the market, for example, as a secondary use to Epic Spot, or something like ancillary services to have the grid stabilized. And this distributed battery swarm is realized by software agents. They have some autonomous characteristics, and they show the characteristics of a fast and robust optimization. And this was taken to the field. And some important findings from this are, of course, that when coming from agent-based simulation to the field, of course, we typically reduce the autonomy of the agents, because there is this industry partner, and we have to guarantee that these local goals always will be fulfilled, that the constraints that are given will always be reflected. But nevertheless, we were able to work with this distributed battery swarm for a secondary use in the field, and that is quite nice. So this is already out there, and our industry partner, B-Storage from Germany, they are especially focusing of large-scale batteries in industry, and they work with the system and even extend it to new functionalities. So the second example, and I will go with this a little bit faster, shows what happens when even more money is involved. Let's keep it like that. So it's an example where we wanted to install agents to a container terminal in the city of Hamburg. Hamburg has a very huge container, very huge harbor actually, and the container terminal Altenwerder is fully autonomized. So you can see it on the card here. That's sometimes interesting for people that already have been there. So at the southern part of the city of Hamburg. And what we see here is this part of the container terminal, and this is fully automized. So here the ships are coming, and what we see here are some kind of automatic vehicles that transport all the loads that come, all the containers, to these kind of areas here, where in the end they will be taken and put on the street or on the train, whatever. And what we see here is that there is this rail terminal. Here is where all the containers come, just to see it a little bit more easier. And all these automatic vehicles that transport the containers, they have been transferred from diesel-fueled to electric vehicles. That is the reason why we have charging areas now in this container terminal. Some are here and some are here. And of course, that is interesting again, because now we come from the logistics area of container terminals to an electrical area where we have a charging. So this is a coupling point of logistics and energy systems. And we were interested in, could we get some flexibility out of this system that is beneficial for the energy system in the end? And you see here that we were able to take these automatic guided vehicles and have them charged with stuff like this here. These are the charging stations. And we see 90 battery electric vehicles in the container terminal with 18 automated charging stations. And this brings us about 4 megawatt symmetrical flexibility in the system. So this is already quite something that we could address. And we were then discussing with our partners, could we somehow work with this flexibility? And that is actually something that we set up in the end. And I go back one slide to give the very short story here first. I already said this is what happens when even more money is involved. You always have to think about where it makes sense to go for distributed system, and it makes sense to even go for autonomous agent-based systems. And here we saw that a distributed optimization is very nice because it shows good characteristics in terms of scalability, and it's very fast. So we were interested in that characteristics, but it actually did not make sense to put agents on these automatic vehicles and let them drive around and find their charging stations themselves. So we see here that we connected the different paradigms. So still, of course, these vehicles are able to drive around autonomously, but the charging process in itself, it takes place here in these stations. And you see here, we have 18 automated charging stations. So that is something that still can controlled without any problems by a central system. But the optimization of how the flexibility from the batteries that are behind these charging stations can be used in the energy system, so delivering this 4 megawatt symmetrical flexibility, that is something that we optimized with a distributed optimization approach in the end. So this is an example, no agents out there in the field, but only the distributed algorithms being involved here. We started off with a different approach, but this is what happens when you come out to reality. Then you have to get the best solution for the field, of course. It's not about installing your approach everywhere. Okay, I will go over this a little bit faster, heavily animated, sorry for that. One last part that is involved here, a very short example of flexibility. So here we're talking about flexibility that comes from the charging stations that of course do have the duty to charge the autonomous vehicles when they come to the station, because they are definitely needed again then to do their duties in this automated container terminal. But the remaining flexibility that is in these charging stations and with the batteries behind can be modeled and have this now involved in the algorithm to present this symmetric flexibility to the energy system. What we found out here is that modeling flexibility has to be specific for the use case that you want to develop it for. And in the last years, we actually had a look at very different flexibility models, and all of them were kind of specific for the use case. One of my doctoral students developed an abstracted flexibility model for batteries. And this is something that can be used for battery use cases very, very well, especially in this dual purpose settings or multi-purpose settings. When it comes to other components in the energy system, a specific flexibility approach might be applicable. So some learnings in this area of flexibility model as well. So before I come to the data aspect, and that is the last part of my talk and very, very short, a wrap up for the agent-based part here. The vision behind that is larger actually. So we're thinking about AI-empowered energy systems in such a way that we still want to have this fully decentralized, decarbonized, efficient, and resilient operation of cyber physical energy systems. That would mean something like, as in the example shown now, the distributed provision of ancillary services. This can be done by our battery swarm that we implemented, but we of course see other possibilities. For example, a colleague of mine works on cyber resilience strategies and how agents can actually learn the cyber resilience strategies in this field. Another colleague or doctorate student of mine here is working on anomaly detection in this field. Quite important, of course, to be fast in reaction when some problems occur. And as I already said, self-organized aggregation is something that is quite interesting for me. This is the area of collision formation that can, for example, be used for stuff like virtual power plants or the cell-based view on energy systems, where you only take some part, a neighborhood or an energy community, and try to optimize this first. So many different applications for artificial intelligence on the one hand, but for distributed algorithms on the other hand. Okay, so what comes next? Actually, we are now working on so-called observer controller schemes in this area. That is one approach to get a better resilience of these systems. I will not go into detail here. That's just maybe as a note, if you come across these systems or are interested, I would be happy to discuss this. Okay, so now I come to the last part on data, and I promised it would be something about pain. Why is it about pain? I come back to this vision. I reduced it a bit. There's no new information. I just reduced it. So actually, we talk a lot about learning systems in energy. So machine learning or learning systems for optimal power flow, learning constraints, learning forecasts. So a lot of learning is involved, and you see here that I simply marked where I already had learning here, and all of that is about data. So we definitely should be able to collect and tag data in such a way, document data in such a way that other researchers would be able to work with these data, and that would be able to compare our results from this field. Then I come to simulation. Of course, if we want to simulate these kind of systems, we need input values, we need the modeling, we need parameterization of our simulation models. Again, this is a topic about data, and doctorate students in their first years talk mostly about where should I get my data from? How can I use them? And the last thing, when we went to the field, preparation for the field is about data as well, because we somehow have to understand what are the power grids that we want to go to. How can we best work on our systems before we go to the field? So data in energy systems are not only time series, although that's typically what you think about first. Of course, it's about data sets like time series or demographic data, but data in energy systems, of course, is something like software as well. So grid computation frameworks, co-simulation frameworks, whatever framework or paradigm in simulation you want to choose, this is an artifact that should be taken from one person to another, because a lot of lifetime, and lifetime is precious, is spent on preparing this kind of software. And we have models, so models are data in our standing as well, and scenarios. Scenarios are very important because we want to compare our work to the work of others. For example, if you from your group have one example, and I'm very interested in your publication, and I want, of course, to compare my approach to your findings, I would not only need your data sets and the software that you had and your models, I would need the scenarios as well. And in the end, of course, a lot of people meanwhile publish their software and publish their data, but when you try to really replicate what has been done, you need detailed simulation configuration, and you need in detail knowledge on how this software has been used. Typically, this is still only working from head to head, so you would have to visit the other research group to come to the same results. So that is still something that we have to work on. So data are more or less the huge group of digital objects, and we are still at the very beginning of a so-called fair universe, where fair is something like findability. So I know that Kirchhoff has built this very nice model somewhere in the history. Accessibility, so I would be able to really get a grip on the digital object that is out there. Then interoperability, so my data or my software fits with these other data and could be put into a simulation framework, so that would be interoperability. And the last thing is, of course, reusability, so I'm able to actually reuse and then in the end replicate what has been done before. So that is a huge vision, and it's really stretchy to come there. Okay, so we are working on this topic of fair energy research data in a huge consortium now in Germany, and doing some work, of course, in the international area as well. But fairness is still to come. So our goal here is to help the community to publish their data, so digital objects from all the kinds that I presented, in such a way that others can reuse. And that is something that is always thought about in terms of being efficient with the money that you get. So a lot of time spent, a lot of money spent to generate data. I always think of it in terms of spending your lifetime, because especially for the doctoral students, if you spend so much time on setting up your simulation models, and some other person already did that before, so how great would it be if you would simply be able to reuse what already has been produced out there before you came in a different working group and at a different part of the world. Okay, so that was my talk. So I talked a little bit about the challenges in cyber physical energy systems. I gave you some examples on multi-agent systems in the field, and in the end, I gave you a very short introduction to the topic of fair data in energy systems. And I'm very, very keen on your questions and ideas on these topics now. Thanks.
Thank you very much. Any questions from here? Yeah, Mike.
And I was interested in the kind of Hamburg porting. Like in that kind of scenario, you have a lot of different timescales at play. You had a graph where you were kind of looking at response in 15-minute intervals, but you've got the busy time when there's ships coming in. Then you've got there's a cycle of ships coming and going, which is over like a course of days, and then you've got the energy load on the local grid, which is an annual kind of time frame. How do you? I guess I'm not very familiar with these kind of the agents kind of base, but how do they cope with like all of these different frequencies that need to be managed? Do you need to make them aware, or does it actually work just kind of naturally?
Mm-hmm. Thanks for the nice question. Actually, my answer is twofold. So when we first have a look at the simulation part, so let's take the part where we develop these kind of systems. Then this is a co-simulation issue, of course. So we need the right scheduling of the different simulation components in such a way that they are orchestrated depending on the different timescales that they are working in. So this is simulation theory that helps us to set up tools and frameworks that are able to solve these kind of or address these kind of co-simulation challenges. But I think that maybe your question goes more into the direction, how does the agent in the end handle this problem in the field? And that is a very nice question, because we always try to set up the agents in such a way that they are not even aware of these different timescales. So the task that the agent should solve should be reduced so much that it does not have such a complex task to solve. But that is something that is completely different than from when compared to a central system. So a central system would have to take into account all these different time scales, while a distributed system or decentralized systems would force you to, during design of the system, try to separate the different parts of the system and reduce the task in such a way that the complexity is reduced in terms of optimization on the one hand, but in terms of different timescales as well. So the logistics system is completely separated from the charging system, and they only have this point where they connect, and these are the requirements when this, the exact requirements when the charging, the automatic vehicles have to be loaded. So that is the only interconnection point of these systems then.
Cool, thank you.
Thank you. Any other questions? Yeah, go ahead.
Interesting talk, thank you. I am not coming from this field, so maybe this is kind of a naive question, but in kind of the area of agent-based modeling, there's this notion which you mentioned, right, where at the intersection of complex systems, you have this property of emergence at the global level. And you talked, Keshav had a question earlier about how you kind of align all the agents in the system so that they're satisfying kind of the global optimization problem, constrained by the fact that they have to first attend to their local optimization. I wonder, you talked about kind of communication and being able to kind of check in with the global procedure. In agent-based modeling or in kind of these agent-based systems, you don't really have them looking at the extent to which the global properties look correct, right? It's just kind of an emergent phenomena. So can you kind of design local optimization procedures such that you just as an artifact of everyone optimizing, their thing locally in a particular way, you get the kind of the global emergent phenomena that you'd like to see?
Mm-hmm. Thanks for the very nice question, and thanks for digging deeper into this direction. On the one hand, this is a question of whether these kind of systems are able to approach the global optimum. That is one part of the question. And of course, if we are in this area of fully distributed algorithms, we are typically in this area of heuristics, and the heuristics come with some specific problems, let's say problems in that sense, for example, that they some of these algorithms tend to be stuck in local minima or local maxima, whatever. So local only a local optimization would be possible then. So that is one problem that could be encountered. Of course, there are approaches how to solve that. So for example, there are a lot of examples of algorithms that are definitely able to come to the near of the theoretical optimum. So that is something that would be interesting here. But the question now is, do we really need the theoretical optimum for these kind of systems? Or are we just interested in a viable solution and in a fast solution? So we do not always need the global optimum when we are in a real world system. That is something that in our mind we tend to think, of course, if there is an optimum, a global optimum, we want to approach it, of course, but actually we do not always need it. So that is one thing. So we can weigh what is more important to us. Is it robustness, no single point of failure, or is it the global optimum? So that is one thing. The second aspect, I just have to think about, lost a bit track. I should have taken a note.
Actually, if I can, I'm afraid our next group is coming to use the room, but we'll need to break it. Emilia, could you, I'll give you the email address to Astrid. You could perhaps continue this conversation over by email. I also have to send you by email, but I'm sorry, we do need to stop here. But
yes, of course.
And let's thank Astrid again. Okay, great. I'm so sorry about that, but we do.
Okay.